So what I'm going to do is, I'm going to do this assignment, like right here. I'm going to do it right here with you guys in front of you. And I'm going to show you the methods that I use to figure out how to do stuff. Okay, so first of all, I'm going to read the assignment. I'm going to figure out what I'm going to do. I have to make a list of the things I have to do. And then I'm going to try and figure out how to do them. And then I'm going to do them. So let's just do that. Okay, let's figure out what we have to do. So, okay, so BJ, I'm just going to fly through this. Okay, so we got to do designer's duties, documentation style, assignment structure, cover page. Cover page. Oh, wait, that's not a problem because I already have some document somewhere with a cover page. I'll just use it. Yeah. And then calculations. Oh man, I gotta follow the procedures. Yeah. Okay. So whatever. Let's go on here. Calculate. Okay. Calculation steps, circuit schematic, submission instructions. That's it. Okay. Cool. That's it. So now I'm gonna go through and see what's going on here. The report with detailed design and calibration circuit MPG. Okay. Designers voltage circuit outputs. One of the transducers. Blah blah blah. This. Okay. That's the This is a list of the transducers and what their parameters are. I don't know why there are 3 of them. Whatever, we'll figure it out. I have varying output voltage. It was these are the okay. So calibration of the circuit so that vibrations circuit design options. Oh, these are the functional parameters. Okay, these are the operational parameters. Do you know what? I'm probably going to write those down. That'll be the first thing. Let's just keep going here. Circuit design students can select any 3 of them. Okay, so that's what it is. So there are 3 of these things, and I can, as a student, select any one I want. Okay, that's good. If students wish, they can do offset. All right, I remember Lars was talking about something called offset. He said it was like really cool, but kind of difficult. Dude, just sounds cool. I'm gonna think about that just like after I finish everything, and then I'll be like, maybe I can throw offset in because you know what, this whole thing wasn't so bad, and then it'll be really cool to study offset. Okay, good. So documentation style, handwritten circuits. Okay, that's cool. I like that. It gets me going. I don't have to spend time. Blah 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 blah. Most professional mathematical documentation. By the way, guys, I was thinking. I did say in lecture that I just want you guys to just do this. But you know what? For me to mark this, and no, I'm not being lazy. Like I need you guys to. Whatever. I just for me to really truly see what's going on in your brain, I need you to document your math on the computer. Okay, so just do it on paper and then spend the extra, hour, half an hour, or whatever it takes to actually put it in the computer using subscripts and superscripts and doing all that. But you know what? In the end, it'll help you when you go back to study this material. If you ever do, it'll help you follow it. It'll help anyone. The point is, it'll help anyone read and understand what you're doing. If you just do it on paper, everybody has different fonts with their fingers and the way they style it, they write it. It's all about how your hands work. Everything is different. Standards are so very important. So I want you to do it on a computer. I know it's a little extra time. Okay, so but you got to do it. Must be include the order cover page. Okay. Calculations. Okay. Drawing. That's it. No appendix. No nothing. No whatever. He doesn't even want an appendix with rough work. Do you know what? I'm probably going to put one in anyway because, I don't know, I'm probably going to do this by hand anyway on paper. Say, subscript, okay, that's right, okay, that's fine. Calculation steps, yeah, I know Lars is ranting on about it. I know what he rants about. Okay, good. So, calculation steps, okay, so these are the steps. Okay, that's cool. You know what, I'm going to copy this. I need that. I'll tell you why in a minute. Because these are this is part of what I need to do. Remember I said I need to know kind of what I need to do, and then I figure out how to do it. This is actually part of how to do it. Circuit schematic. Okay, so whatever. You know what? I'm not even going to read this because I know if it says freehand, that's fine. I'm just going to know when I draw my circuit schematic. After I draw it, I'm going to read all of this and find out exactly if I'm missing anything. But I'm not going to miss anything in my circuit schematic because I'm going to make sure I label everything and draw everything so somebody else can at least understand what I'm drawing. And doing this graph paper. Oh, right. Yeah, no, it's stupid. People that use graph paper are... Submission instructions, submit MS Word. Okay, cool. Okay, so that's what I've got to do. You know what? And this is how I started things. I started a brand new document. Now, I should probably actually just start these notes in your document. Go to your file that's got a cover page already. Hold on, I'll go get one. Okay, so I grabbed the report structure assignment that one of the students did. And then what I'm going to do here is this cover page already exists, so that's nice. And then I'm just going to put my name in here, my student number, and the date, change the date, and change the course code, whatever. And then table of contents. Ooh, nice. You know what? I can just go. Because, you know, report doesn't ask for one. Introduction doesn't ask for one. Okay, good. So, very good. The title page. Actually, I put page numbers in. Actually, let me go. Hold on a second. Insert. It's always good to put page numbers in. I like at the bottom of the page, bottom right. It's more better. Okay, good. So on the first page, I got nothing. Okay, circuit schematics. You know what? I'm going to leave this. I mean, it's not whatever. I'm just going to say circuit schematic, and I'm just going to back that up a bit. And then what I'm going to do is when I do my assignment, I am just going to then I'm going to right click on this, and I'm going to say. I'm going to say change picture, and I'm going to go into the wherever I take a picture of my drawing that I did, and I'm just going to click this and change the picture. Nice. Whatever. There's a comment. I'll leave that there. Maybe I'll change it later. Formulation. Sweet. Okay. Good. Formulations. Now, part. Whatever. Let's just go for formulations. Okay. So at least I have some titles and stuff like this. I don't know what my formulations are going to be. Like I don't even know, but I just know that. I'll probably take a couple of different formulations, so I'm going to leave this here, and that's good. And conclusions, recommendations, nope, that's it. Appendix, whatever, references, nope. Appendix, yeah, you know what? I don't know. I might just find a data sheet later. Good. So I got something to work with. Now, you know what I want to do is, I just want to go here. Hold on a sec. I'm going to go here. I'm just going to go here. I like this no spacing really to work with for my notes and everything else. So what I did was I took this from let me go back to the assignment. So I got the assignment, right? Here's the assignment, right? And these seem to be the functional requirements. So and this as well. So what I've just done here, since you select anything, I know this. I just want to write stuff down that I need to know. Okay. So I've just copied this. Let me just copy this. Copy this, and I'm just going to put this right in here. So now, let me just see. These are the sensors. Okay, so have a varying. Let me just go here. Have a varying calibration. I'm gonna kind of dumb these sentences down a little bit, right? Okay, hold on a second. Okay, so these are my three. You know what? I'm gonna choose which one I'm gonna use right now. Force sensitive. Okay, LDR and thermistor. You know what? I'm not going to do that right now. I'm just going to do this. So have a varying output, lowest value. Okay. So now what this means, lowest value of 0.2 volts and highest value between. Okay. Let me just figure out what this means. Let me go back to the PowerPoint to figure out what this means. Okay, here's the PowerPoint. Okay, now if I go study this stuff, what I'm going to find out, what you're going to find out when you study this stuff is that when the sensor is at either its maximum or minimum, depending on whether it's up here or down there. And so I'll have to see in the assignment whether I'm supposed to put it up here or down there. And then my output's going to vary. But I know that the whole thing about this is that, hope this makes sense to you. When your sensor, when the transducer is producing the lowest amount of voltage, or actually maybe the highest as well, depending if you put it at highest, lower. But when your transducer is at some maximum, either all the way low or all the way high, then you want your transducer, your transformer, no, your transistor, to close, okay? So at some maximum of the transducer, you want your transformer, okay, you want your transistor to close, right? 0.2 volts. So that's going to be my maximum. So here, either I do it like this, or I'm either going to do it like this or like this. So that's my decision. I have to think, let me just see if it is my decision. Calibration sensors, okay. Variable output, very simple. From the lowest event, ooh, no, it does specify. The lowest event. So remember, events are just things that happen. Right? So in this case, the lowest event would be if I use the force transducer, the lowest event is the lowest force possible. So ranges 12K to 200K. Okay, so when it's at 12K, when it's at lowest resistance, that's when I want 2 volts out. Okay, in this case, the lowest resistance, so the lowest event is when the resistance will be low, because transducers, they just take an event and turn it into an electrical impulse. And if the event's not there, or if it's at its lowest amount, the electrical impulse will also be at its lowest amount. Okay, good. So now, so that means that in this case, going back to here, variables of the lowest value is the highest value. Okay, but it specifies between 10 and 18 volts. So my VCC is going to be higher than 10 or 18 volts, and I'll explain that in a minute. But I know that. Okay, so I'm just going to take a circuit, and I know. See, these are my parameters. I know that at my lowest resistance, I want my BJT to be closed. Okay, cool. Okay, that's good. So lowest BJT closed. Okay, lowest. I'm just going to dumb this down. Lowest event equals BJT closed. Whatever. My fingers, dude. I know how to spell the word closed. Okay, value 2 volts. Highest value events between. Okay, so output. Output between 10 and 18 volts. So it's my choice. Okay, that's fine. So I've just dumbed this down to as simple as a calibration circuit. The variation of the output voltage corresponds to the variation of the event and inconsistencies in the transistor's resistance in BJT and gain. What is it? Inconsistencies in transistors? Yeah, that means in between some transistor and another transistor. And when you buy a transistor, it's going to change. So essentially what this means is that you have to put variable potentiometers in here. Okay, good. And also the gain's going to change, right? And that's why we need variable pots as well, because the gain's going to change. Okay, so you know what? That's fine. It just says the calibration of the circuit, calibration variable. You know what? That's fine. It just means put some BJTs in, dude. I mean, what do they call them? Potentiometers. Okay, options. Have an offset. Oh, that's it. Dude, wow, I cleaned that up. So this is my big deal here. Okay. So my formulations, let me go back to the, okay, so I've dialed this down to, I have to choose which one of these I'm going to use. LDR, do you know what? Let me just show you on the screen here. I got a bunch out. Hold on a second here, guys. So this is a force-sensitive resistor. That's what they look like, and they're really cool. And this one's flat, and this one's flat, whatever. Square, I mean, that's round, and that's long and thin. And these are pretty cool. So I get a pack of 26. You know what? I might even want to pick one of these up. Amazon will be here the next day if you got Prime. But you know what? I actually have some of these. If you want to build one of these in the lab. Actually, I'll try and remember to bring some. Okay, so that's that. Now, the other thing is an LDR, a light-dependent resistor. So these guys themselves, what happens is their resistance changes when I put light on them. It's actually really, really cool. So, and the parameters here are such that, 5 and 10 kilo ohms. Oh, okay, so, okay, so the light resistance is 5 to 10 kilo ohms, and the dark resistance is 500 kilo ohms. So it goes in between 5 to 10 kilo ohms to 500 mega ohms. Okay, good. So there's a kind of variability there. Like, you know, it seems that the lightest, when it's the brightest, the resistance is in between 5 and 10 kilo ohms. Well, the thing is, when it's super dark, it's going to be 500,000. So whatever. I'll calculate. I'll do the math with 7 kilo ohms, and then from there just calibrate. Now here we go. Here's a thermistor. Thermistors are really cool, and what they are is they're just that's kind of more of a simple one here. So this strip is sensitive to resistance, or sensitive to temperature. The resistance changes. So, and actually, let's take a look at the resistance changes. Here we go. Does it say? Whatever. I don't know. Whatever. I mean, I should be going to DigiKey or something to actually get the proper parameters. Two can be used as something. Port. Oh, here we go. So 100K to 1.9 kilo. 1.9 mega ohms. So 100 kilo ohms to 3.9 kilo ohms. So there's I mean, a huge differential in resistance. Cool. So I could use this one. Now, it says, actually, in the assignment, it specifies, you know what? The one with the greatest range is going to be the one that's really going to work for me. So in this case, when the range is for 10 lux for dark. So essentially, in this case, when it's really, this is kind of, let's use this one because it's kind of more difficult to use. When the event is at its lowest, that means it's dark. I mean, the event is it's getting brighter, right? When the event is at its lowest, it's dark. And when the event is at its highest, it's 10. So you know what? I'm just going to take these guys. And I'm going to do LDR. And I'm going to take this. And I'm going to put this in here. So now, I have to think about it. It says specifically that when the event is at its lowest, okay, so this is at its lowest. Okay, so you know what? I'm going to highlight this. I'm going to do this just for my brain. Okay, that's low, and then this is so that's dark. Sorry, this is dark. This is dark. I don't know. Dark is green, and then bright is going to be yellow. What's this? Kiloohms. Kiloohms. That's just my typing. Okay, good. So now that's bright and that's low. So now what I got to think about is that I have to actually start designing. Good. So I'm going to take... Stop that, you dumb, stupid, dumb. Bad. Okay, here. Start designing. I know that my BJT... Let's just take a look at my BJT. My BJT will be closed when the current's at its highest. The current's at its highest when the voltage is at its highest. So when it's the darkest out, the voltage into my BJT has to be at its highest. Okay, so let's just go back to here. When it's dark, I need the highest voltage when it's darkest. Okay. So if I put my LDR down here, and at its darkest point, it's going to be, that's going to be at its highest resistance. So the voltage drop will be at its highest. Okay, so the voltage drop is going to be at its highest when the LDR is at its darkest, and the voltage is going to be out, which means that my BJT will be fully saturated. When it's brightest, when it's at its brightest, this is going to be only 10K or something. And then the BJT, the voltage out will be very low. And then my BJT will open up. And it will be open. Now, when it gets open, it's going to be open to like, I don't know, 10 volts or something. You know what? I probably use an Excel sheet for this. But for now, let's just try and do the math. And then maybe I can, after I get the formulas, maybe I'll throw it all on an Excel sheet and I'll play around with the numbers to see what my VCC should be. Because I have to choose a VCC here. Because my output has to go between, I don't know, 10, let's take a look at the parameters. What's the parameter for the output again? 10 and 18 volts. So I have to choose my VCC so that that happens. So I can crank the VCC up to 100 volts if I want. I mean, you shouldn't do that. But I can crank it up to some value so that I can play around with the numbers. Excel sheets are amazing that way. You type in a different value and see what happens. Bing! It goes, and it does everything. So with that said and done, let's actually start designing. You know what I'm going to do? I'm going to take this, I'm going to go to the PowerPoint that Lars drew, and I'm just going to copy this. You know what? I'm going to go take a look at this. Because it was one, yeah, this one had, by the way, guys, I fixed this. I'm going to copy this. I'm going to go to here, and then I'm going to crop, and then I'm going to just print. I'm going to physically actually print this. Yeah. And the reason I want to print it is so that I have it beside my drawing. Not my drawing, my calculations. And then I can redraw this. This, I mean, you know, whatever. I already drew this for you guys, so you can just work with this. Good. So now I'm going to change the camera so that you guys I'm going to do the work down here. So let's start from here. I'm going to use an LDR. And what I did was I took this guy and I copied that, as you know, from the PowerPoint. And then I also copied these two circuits as well, because they're going to help me understand where I'm going to be putting my LDR, whether it's going to be up here or up here, and how does that matter. So essentially what's going on is that it's all about the parameters here. Lowest event equals BJT closed. Okay, so the event is that it's getting brighter. So when it's not bright, it's dark. So therefore, when it is at its darkest, I want the BJT to be closed. So when it's at its darkest, the resistance is very high. Okay, so let me just see if I should use this one or this one. I've already just talked about that in the video, but I just want to go over that again. When it's darkest, the LDR is going to be at its highest resistance. So dark equals high resistance. It also needs to equal voltage high as well. The voltage has to be high when it's dark, because if we take a look at this, if the voltage there is at its highest, this becomes closed, and the voltage drop from here to there is going to be very low. It's going to be 0.2 volts. When it's, remember, when I have the most current through here, this becomes closed, and the voltage drop across goes to 0, or 0.2 volts. When this gets low, this slowly opens up, and my voltage here increases. The voltage out increases. So what I want to do is I want to make sure my LDR is either here or here, such that when it's at its darkest, this is at its lowest voltage, and when it's at its brightest, that's its highest voltage, okay? So when it's darkest, the resistance is highest. I need the highest voltage here when the resistance is highest, so that the highest current can be here, so that's closed. Okay, so I have to put the LDR down here, because at its highest, if this is 500 here, if this is 500, and what are the parameters here? Oh, it's 350. So 350 kilo ohms. Let me just write that here. So I'm going to put the LDR down here, and that's going to be 350 kilo ohms. And then up here, I'm going to have my calibration resistor. So I've got this here, so I can look as I'm developing my formulation, so I can see a circuit. Okay, good. So I'll just work with this, although it's a mess. Let's roll with it. So I got this guy over here and this guy here. So what do I do first? What do I do first? Well, essentially, what I want to do is I need to know the current through here, so that I can know the current through here, so that it's going to saturate. To know the current through there, that means the voltage that's here has to be at its greatest. When is it at its greatest? When it's darkest. Okay, so the first thing I got to do is work this way and work like that. So the first thing I have to do here is actually I have to put the calibration resistor up here and figure out what it is. Now there's a formula for that. So RCal equals, this is my first formula. This is the resistance of the transistor minimum squared times the resistance of the, let me go back to the PowerPoint just to make sure that I'm getting it right. Okay, it's always just good to have the PowerPoint open and then work with that. So now let's go up here and see what this is all about. See if I've got this here. Yeah, there it is there. Oh, it's not squared. Okay, it's good that I went and checked the formula. Yeah, dude, the formulas are always there. Okay, good. So that's the resistance of the transistor minimum. And you know what? I'm just going to throw in the numbers in my calculator. Actually, I should write them down because this is my rough notes, right? So this is going to be 3. So that, you know what? What are the parameters again? Sorry. 10K to 350. Okay, let's go with that. So that's going to be 10 kilo ohms squared. No, it's not squared. Stop throwing it. Times 350 kilo ohms. And that is going to be, okay, let's do that. So bracket, whoops, clear. Stop that. And then I don't need to put brackets here because my calculator already knows. So I'm just going to go 10 kilo ohms times 350 kilo ohms. I just had some tea. Dude, everything makes me burp. Okay, good. So there we go. So that's 59.16079 kilo ohms. And I'm gonna put that in R. I'm just gonna save that in R. Elemental PQR. Done. Good. Whoa. Go to. Good, so that's in R. So I have that value and I can pull it up anytime I want. It's in R. Now, okay, so that's fine. So what I'm going to do is I'm going to put this resistor here. This is my calibration resistor and it's going to be 59 So, you know what, to do that, to get 59 exactly, I'd probably go and get a 51 kilo ohm resistor, because they're available, and then I'm going to go get a 10K pot, a 10K trimming pot, and just turn it and calibrate it. So it's going to look like this. Actually, let me just draw it this way. So far, the circuit looks like this. I've got my power coming in here at 5 volts. You know what, it doesn't say whether it should be 5 volts, so I'm just going to assume it's 5 volts because that's what the PowerPoint lesson says. That's my calibration resistor, and then that's my output. So this is my VBB, and down here is my LDR. Now, what does an LDR symbol look like? Well, I don't know. Go look it up. Just Google it. You guys should be using the right symbols. I don't think I have an LDR in the I did have these up. Where did it go? In the PowerPoints, in the lessons. So let's just go find out what an LDR looks like. Nothing like Google. Yeah. So essentially the way I draw it is I just do it with a circle. So that is a resistor, and then I put a circle around it. So now this guy here is going to be 59. So what I'm going to do is I'm going to put a 10K pot here, 10 kilo ohms, and then I'm going to, right here, I'm going to put a 51 kilo ohm resistor there, because you can get 51 kilo ohms. Well, I mean, they don't have them in 50s, but they come in 51s. It's weird. I don't know why. But anyway, you can probably get a 50 as well. But, I mean, you'll have a 51 in your kit, or easily accessible. So you get a 51 here, and then this, and you can adjust this. That's 10K. You can adjust that to that. You might put a 20K in there, or actually 51. Yeah, you'd be right. Whatever. So that's that. So that's there. So that's LDR. And just so I'm good, I got my numbers up here. I don't have to label them here. So let's move on. So I've got this. So I know what the value there is going to be. Now I need to know what the maximum value in and the maximum value out is going to be. So when this is at 350 kilo ohms, what's the V? Here we go. This is VBB. So I'm going to say VBB max and VBB min. So I'm going to calculate those. Okay, VBB max. VBB max equals when this is at its highest value, and that's at its, well, that same value there. So that's going to be the VS, so that's 5 volts, VS times that, in this case, it's just a voltage divider, right? So I'm looking for the voltage drop across this. So that's the resistance max, and then that's going to be over the addition between the two. Resistance max plus, now if you should be writing better than I'm writing, because I actually want to read what you're saying. I'll pretend that I can write better. Okay, and then this is going to be 50, you know what, I'm just going to say, because it's my own work, plus resistance R. So now I'm going to be 5 volts times 350 kilo ohms, and that's 350 plus 59.16 kilo ohms, and that's kilo ohms. And so I'm just going to put that on my calculator. Okay, so I already have this number here. Do you know what, guys? This is what I do, because I don't want to have to, even though I can memory recall R, I'm just going to do this. Plus 350, 3 equals. Now I'm going to divide that by this, 350. Now that was the inverse of what I needed to do. So I'm going to hit inverse, and then I'm going to multiply it by 5. I'm done. So that's 4.277 volts. So that's going to be, I'm going to store that in, that's a maximum. I'm going to store that in M. Dude, it's really, really amazing to have a calculator where you can store these things in. It's ridiculous. Element O, LM. Good. So that's it stored in M. Now I'm going to do the VBB minimum, and I'm not going to write the formula. I'm just going to put the numbers. 5 volts, 5 volts times, in this case, it's going to be 10 kiloohms. That's 350 kiloohms plus 59.16 kiloohms. Okay, good. So now I'm going to reuse this. I'm going to use R. So I've got 5 times 10K divided by 10K plus R bracket equals. Good. So this is nice. Look at this. It's really, really, really low. Ooh, dude, look at that. It's exactly 0.7 volts. That's awesome. Like, that's really awesome. I think it, you know what? I might even have a problem with that. Because I need, right here, I need at least, right here I need at least 0.7 volts. But the voltage here that I've calculated is 0.722 volts. So I've got 22 millivolts to work with. The voltage drop across that, it's going to be 22 millivolts. So let's just see what we can do. Let's roll with that. Let's see what happens. Okay, so I've got this. What was it? It was 722.95 millivolts. And I'm going to store that on, that's maximum minimum. I'm going to store it into an N. I'm already storing something in an N. No, N. I'm going to store that in N. Okay, good. So I'm storing this in N, elemental P, M, N. Good. So now I've got, I'm just going to highlight these numbers. I've got this guy, and this guy. Those are the most important numbers I've done on this page. So now I'm just going to put this aside. Maybe I'll pull it out later. Actually, I will. I'm going to put it over here. Good. So now, let's do this. I need to know how much current is going to go through here so that I need to know how much, so that I can find out how much current is going to go through here so that I can find the resistor that I need there. Now, the thing is, I don't have the gain. I'm going to go back and find out what the gain is. I'm going to go to the original document to see if there's something about gain in here. And if there isn't, then I'm going to email Lars and say, Lars, what are you doing, man? There's no gain. Oh, gain is 100. Okay, cool. I can work with that. Okay, cool. So I'm just going to write the gain equals 100. Okay, so the gain's 100. I can just work with that. So now, dude, I'm at the point where I don't know what to do because I don't have a voltage here. I don't have a voltage. So, like I said earlier, I was going to do an Excel sheet. And I will end up doing that to play around with it. But let's just go with this. Let's just go with some value here. Do you know what? My output needs to be between 10 volts and 18 volts. Somewhere in between there. So if I made this thing, remember I'm going to have a voltage drop across that. So I'm going to need to, when this is wide open, when that's not wide open, it's not, when it's wide open, it's going to be actually whatever the voltage is here, that's what I'm going to see here. But I'm not going to be able to completely and entirely open this thing when this goes to its lowest resistance. By the way, guys, heads up. Let me say that again. When this goes, let's just go down here. When this goes to its lowest resistance, the output here will be very low. And then the voltage here is going to be even lower than this. What was I looking at? Oh, right. No, I'm okay. Okay. Yeah. It's going to be really low. Okay. So when that's really low, actually, this is really perfect. These numbers worked out so well. Like, really, really, like, oddly well, dude. Oddly. That's maybe because I probably designed the numbers to do that. But what I'm saying is that when this is at its lowest, it's going to be 0.7 volts, which means that this is barely going to be open because the current's going to be so low. I mean, barely going to be closed. The current's going to be so low through here because I only got 0.7 volts here. The current's going to be so low that this is barely going to even be closed. So I'm assuming that that it's probably going to be close to whatever I put there. So you know what? I'm just going to put an 18 there. I'm just going to put an 18. If I could put a 20 there, but I might even get 19 volts out. Let's find out. So I'm going to say VCC equals 18 volts. Now, if I get maybe 17 and a half or whatever, it's okay because the parameters say that it's the output somewhere between 10 and 18. So with that said and done, I want to know how much. I'm going to work with this 18 volts, and I'm going to find out how much current is going through here when this is fully saturated. Okay, so I'm going to say IC is going to equal to, now let's just walk through this with like Kirchhoff's law. There's a voltage drop here at 0.2. There's a voltage drop here, which I don't know because I don't know the current, but I know the resistance. So what I'm going to say is the voltage drop across this is going to be this minus that. Watch this. Let me just put this on the side here. The voltage drop across the calibration, the collector resistor is going to be VCC minus VCE. See that? So I know that I is V over R, right? I is V, in this case, VRC over RC. Well, VRC equals this. So I'm just going to do this. I'm going to say VCC minus VCE divided by RC, and now I can find the current. So that's going to be 18 minus 0.2. Now, because I'm assuming this is when it's closed, I want to know the maximum current here. And that's when it's closed. And when it's closed, it's 0.2 volts. So, and that's going to be 10 kilo ohms. And let me write that in here. That's going to be 18 minus 2. So that's 17.8 divided by 10 kilo ohms. And that is 1.78 milliamps. And that's fine. It's an even number. I don't need to put it in my calculator. That's that. Okay, look, you know what? That's fine. That's a number that I'm after. I'm gonna just do this. Okay, that's a number that I'm after. Now, if my gain is 100, then my IB sat, the saturation current to make this thing close is going to be 100 times less than this. So I'm just going to divide this by 100. I'm just gonna write I sat is IC divided by 100, and that's going to be 17.8 microamps. 17.8 microamps. Again, that's a number that I need. That is a number that I need. Okay, good. So I now have the current that I need to go through here to saturate this. So now I know the maximum voltage there. When I want this saturated, that's when this is at its maximum voltage, when it's darkest. So I know what that voltage is. That voltage is here, 4.277, and I've got that stored. So what I want to do is, I want to select a base resistor. Base resistor, I can read that. So I'm going to say the resistor for the base is going to be divided by, so resistance is current divided by voltage divided by current. So what's the voltage drop across the base? And what is the current? Well, I know what the current is. It's this. The voltage drop across the base is going to be VBB, more specifically max, right? The voltage, the maximum voltage minus 0.7 volts. And that's going to be 17.8. I mean, that's going to be, sorry, IB sat. IB sat. So if I put those numbers in, that's going to be 4.277 volts minus 0.7 volts divided by 17.8 microamps. And that is, now I'm going to pull this from my calculator. So that was stored in M. Just so I'm going to be as accurate as I can. And in the end, I'm going to adjust things, but I need to be as accurate as I can so that I'm reaching a target that's as closest to what I'm after, even though it's not perfect. Okay, good. So I am going to grab M just to check it. Yeah, it's 4.27 minus 0.7 divided by 17.8 micro, and that's going to be 2.957 kilo ohms. Now I'm going to store that in B. Okay, I'm going to store that in B. So that's going to get stored in B. That's good. So again, so these are the numbers I'm after. I want this number and this number and this number. That's what I calculated here. Good. So now let's just find out what we just did. I knew that my maximum and minimum values were 350 and 10. So I took this formula here and I found out what my calibration resistor should be so that I have the greatest voltage differential out here. So I did that, not simple. Now, then what I did was I chose 18 volts. And that was from the parameters of the assignment. I chose 18 volts. So I want my output to be the greatest. So I chose 18 volts. And with that, I then calculated the amount of current going through here if this was closed. So I got that. I got the full current through here, the saturation current. And then I said, well, if the saturation current here is 1.878 milliamps, the base current required to saturate that is 100 times less. So I divided that by 100, I got 17.8 microamps. So if I have 17.8 microamps coming through here, then this will be fully closed and the output will be 0.2 volts. Okay, good. So now I needed to know how much my resistor should be so that I would have that current because I know the maximum voltage. And I know that it's the maximum voltage I'm after because when that's maximum, this is closed and that's going to be 0. Good. So now I got that and now my base resistor. Excellent. So I've got these values. So I've got my base resistor and I've got that. So what do I do next? What do I do next? Well, I'm going to actually calculate the V out. Now, I'm just going to say this. V out minimum equals 0.2 volts. I mean, that's just established. I know that that's what I want. I mean, when the BJT is closed, that's that. But I want V out maximum. Maximum. So now, for that case, the BJT is open. So, but it's somewhat open. It's not all the way open. But let's find out what that is. Well, for me to do this, that means that the voltage here is going to be at its lowest. So I know that my VBB minimum is going to be 77. What was it? 777.95. 95 volts. Now I do have that. I'm just going to say that was stored in N, so I can pull it up. So what's that formula look like? It looks like this. I need to know how much current is going to go through the base. So I'm going to say IB minimum. And that's going to be, in this case, again, if I need to know the current through there, I need the voltage drop across this divided by the resistance. So the voltage drop across that is going to be, so VRB is going to be VBB minimum minus 0.7 volts divided by the resistor. 200.957 kilo ohms, which was B. Just putting that there so I can remember. Good. So I'm now going to do the math here. So this VBB here is N. Okay. So I'm actually going to write this down. So 777.95 minus 0.7 volts divided by 200.957 kilo ohms. This should actually be RB if I'm writing a formula down properly. Okay, let's do this. So now this number here is N. So I'm just going to pull N up. I'm going to do, oh, my calculator just turned off. So I'm going to do bracket alpha N minus 0.7 divided by this guy here was stored in B. 114.2796. Whoa. Nanoamps. Nano. And that's because the voltage drop across here is only 22 microvolts. 22 microvolts. So now this BJT is going to be pretty much barely closed at all. So that's this. So again, that's something I need. That's something I need. That's the first number that I need there. Now I want to know how closed this BJT is. How closed is it? Well, I can tell you that by knowing how much current's going through here. So I am now going to calculate IC. IC is going to be the voltage drop across this plus the voltage drop across that. The voltage drop across this divided by the current. By the resistance. Pardon me. The voltage drop across this divided by its resistance. Well, in this case, what I'm going to do here is I want to know what this value is here. So this my IC. My IC. Wait a second. Let me think about this. My brain lost that. So yeah, I want to know how much current's going through here. So this is really interesting. It's actually really basic. It's going to be IB times beta. It's that simple. But I'm going to work with that to find out what the voltage drop is here. So let me just take this. This is 114.2796 nanoamps times 100. So I'm just going to multiply that by times 100. Okay, good. Well, there's got to be there's an answer there. Oh, delete. Okay. So that's going to be 11.4217 microamps. Okay, and I'm going to store that in, let's just say I'm going to store it in A. Okay, so I'm going to store that in A. Good. So that's stored in A. So that's a number that I need. Good. So now what I want to do, I'm going to fit this in here. What I want to do here is I want to find out what the voltage drop here is. Well, it's going to be the voltage here minus the voltage drop across this. The voltage drop across that is going to be this value divided by this, which is going to be ridiculously tiny. So I'm going to say that the V out maximum is going to be VCC minus VRC. That's it. That's Kirchhoff's voltage law for a series circuit, because this plus this equals that. So if I want to know what this is, I take that and I subtract this. So the voltage drop across this plus the voltage drop across that equals this. So I am just going to do that, and then I'm going to calculate this guy by multiplying this times the resistance. So VCC is actually, let me just rewrite this formula again. I'll write it down here. VCC minus, to calculate VRC, I'm going to say IC minimum times RC. And that's it. So that's it. So I'm just going to calculate this. Now VCC is going to be 18 volts minus this, which is 11.4217 microamps times 10 kiloohms. And let me put that math in. Now, I've already got this value in my calculator, so I'm just going to multiply that by 10K. And now I have that number. And I'm going to subtract it from this number, but it's going to give me a negative number, but it doesn't matter. I'm just going to flip the negative around. That's just using your calculator properly. Minus 18 is going to be, this is crazy. This is beautiful. 17.88 whatever, 8857 volts. That is going to be, I'm going to store that in V. So I'm going to store that in elemental PQRSV. Store that in V. Nice. This is amazing. This is truly amazing. The reason it's truly amazing is because typically what I'm going to have is, do you know what? Here, just let me talk to you guys. So the reason this is amazing is because when you're doing these BJT sensors, typically the resistance of the input and output, or whatever, the lowest voltage that's coming out of your VVB isn't going to completely open your BJT. It's not going to completely open your BJT. It'll open it like, I don't know, 3/4 of the way sometimes. Because not a lot of the times is that variation in voltage so great. The variation of the VBB voltage. In this case, it's really big because my resistance differential of my thermistor is so great. So I have a large voltage differential in my VBB, which means that the BJT will have a large voltage differential across the VCE. So in this case, dude, we got this thing from 0.2 volts to pretty much 18 volts. And so let's just continue drawing this and see what the rest of it's going to look like. Let me see if I can do this. So I've got all these numbers in this. So I'm going to put this, you know what, I'm just going to, dude, this is crazy. I'm going to label these things because this is nuts. This is page 1. This is page 1. This is page 2. And then this was page 3. Good, just so I know, when I scan these and I put them in my report. Again, you guys, I don't need to see your rough work. I mean, you know what? Actually, you can, yeah, I don't care, whatever you do. I'm not asking for it. I just want you to I just want you to learn from this stuff. So, there's that, I have all the parameters. So let's just draw this circuit. So I'm going to say the resistance of the transducer maximum is 350 kilo ohms, and the resistance of the transducer minimum is 10 kilo ohms. Okay, good. Now this was, it's actually, oh, you know what? I'm going to put another resistor in here. And I'm going to call, so that's 59, right? Oh, right, that's going to be 51 kilo ohms. And this is going to be a, I'm going to say 10K pot set to 8.16 kilo ohms. Okay, good. So that's my RB. RB is 200 point. Now, you know what? You can label these things 200. So that's going to be a 200. You know what? So I'm going to get I can get a 180. I'm going to get a 180 kilo ohm pot. No, I'm going to get a 180 kilo ohm resistor. Sorry, that's just going to be a resistor. So obviously I'm going to draw this twice. And then over here, I'm going to get a 20 kilo ohm pot set to but you know what? No, it'll be a 190. When you go buy a resistor, it'll be 190. You can get a 180 as well. I'll get a 190, and I'm going to set that to 10.957 kilo ohms. Now, again, dude, when you're actually physically calibrating that, and if you calibrate the whole circuit so it does exactly what you want, if you were to physically remove this, it's not going to be exactly this number. But write them down. So now what I want to do is I want to do this. I just want to draw I want to continue drawing my circuit so that, so it's doing what it's supposed to do. So I'm going to do this guy here, and I'm going to do this guy. Now, the calibration resistor here, I'm just going to maybe make it a little bit here just to see. I'm going to kind of think about the calibration resistor, right? Okay, good. Now, this is going to be my V out. Now, this is my RC, and that's going to be 10 kilo ohms. And that's my VCC, which is 18 volts. Good. Now, maybe you know what, I might even label this kind of like this. Do you know what, let me just see what I can do here. Let me get a blue and a green or something. Yeah, blue and green. Here, blue. So I'm going to do this. I'm going to do that, and I'm going to call this IB minimum. And that was, what was it? IB minimum. So I think you get where I'm going. I don't want to take too much of your time, guys. So I'm going to label this whatever the IB minimum was. You know what? Let's find out what it was. So that would be on page 3. The IB minimum is going to be 11 point. So that's 11.47 microamps. Now I'm going to do this, and I'm going to say IB maximum equals, what was the IB maximum? That was nano IB V out IB minimum 2, page 2. Oh, right, 17.8 micro. 17.8 microamps. Now, definitely you got to label this, guys. You have to label this stuff. You have to label this. So I'm going to say V out max is going to be 17.88 volts, something like that. And then V out, I mean, you don't need to use colors, but I like colors. V out minimum equals 0.2 volts. I don't have to calculate that. Okay, so now what I'm going to do is I'm going to scan these. I'm going to redraw this so it's actually readable by other humans and by myself. And then I am going to document all of this calculation on my sheet. So let's just take a look at that right here. So I can get rid of this stuff now. I can just delete all this stuff. And then, yeah, I'm just going to redo this calculation power of the, I'm going to say, maybe even say step 1 or something. Calculation of the calibration resistor. And then I'm just going to use these. I'm going to just change these around because they're already here, right? My subscripts are here, everything, right? And then here I'm going to say calculation of minimum and maximum voltages at VVB. And then I'm going to do whatever all the steps that I did here. And then just take your drawing that you've done that is better than this and save it to your computer and then just change picture, boom, and then just go change the picture. And then if you want, you can put your rough work in the appendix. And if you want, you can go get a data sheet on some transducer. You know what? If you want, dude, you could go get your own go get your own transducer from DigiKey or wherever you want. Get the parameters and use that. And then put that data sheet in there. If not, you can work with the ones that are on the in the assignment sheet. Yeah. Well, I thought that was good. I think you guys get that. If not, then let me know. There you go. Now you know how to build a sensor. Okay, bye.